Okay, hey everyone. I hope my audio and video is working properly. Please leave a comment if there's any issues. Otherwise, I'll proceed as if things are working. So today's topic is probing pre-trained models like BERT or GPT or these other things that we've learned about to understand what kinds of linguistic properties they have learned in their various layers and parameters and so on. So we'll go over a couple of different methods for assessing the types of knowledge that are encoded by these models. So before we start some logistic stuff, we will go over the answers to the exam on Wednesday. And again, Wednesday's class could be remote depending on if my cough goes away. Hopefully it will, but I'll let you know soon. And your last homework is almost ready. We're just finishing up some last details, and it will be released in the next couple of days. And we'll have it due the first week of May. So yeah, those are the immediate to-dos, and we're starting the exam grading this week as well. All right. So is it streaming all right? I don't know, my OBS is saying that the connection's not very good. If someone could comment saying whether or not they can hear me, that would be appreciated. Okay, so we'll get started with first more visualization-oriented analysis of the models that we've been talking about. So there was this recent paper called Bertology where we were trying to, sorry, not we, but the goal was to investigate the different types of information encoded in things like the attention, the hidden states, and so on. So Bertology is basically just a way to extract different parameters from the model, accessing hidden states of BERT or the attention scores, and also retrieving the values of particular heads and their gradients. Okay, good, you can hear me. These kinds of tools are very useful when you're trying to also make some modifications to these models. So in this paper, are 16 heads really better than one? They find that in BERT, you can actually remove a huge percentage of the attention heads at test time. So not requiring any retraining of the model at all, and your performance is not significantly impacted. And you can, think about how you can find which heads to prune by perhaps looking at the attention distributions of each head with different inputs and seeing if some of the heads are redundant in nature. And if they are, then perhaps they can be removed if they're not contributing any new patterns or insights to the model. So there are other tools that kind of go beyond just looking at the parameters to looking at the gradient, which can be very useful in determining, for example, which words a model is paying attention to the most when it is trying to solve a particular task. So Allen NLP has this tool called Interpret that allows you to make these some sort of simple gradient visualizations to help interpret why the model is behaving a certain way. So I thought we could check that out. Let me go over here. So this is the Allen NLP demo for masked language modeling. This is, BERT's pre-training task. You all should be familiar with this now. And so we can select a sentence here, or we can write our own. I'll just select this one. The woman wept because she was masked. So now I can run this model, and it gives me the prediction for the mask token as crying, dead, not really a appropriate word given that context. The woman wept because she was weeping, also not good. Afraid and dying seem more relevant to this context. But anyway, you might be curious to know when the model was making this prediction of what goes into the missing token, which words in the sentence were most important to make that prediction. And so you can go down here and you see this model interpretation thing. So we can just look at a simple gradient visualization. And so basically how this is done is you compute the gradient of the loss at this mask token with respect to all of the embeddings in the sentence. And then you just take the L2 norm of each of the embedding gradients and rank them. So here it says you're visualizing the top 3 most important words to predicting whatever goes into this mask token. And the top words here were, so wept, that word got broken into 2 subwords, WE and PT. And so it makes sense that wept because were the most important words that the model thought when it was making this prediction. So you can do this for other tasks as well. If we look at, say, sentiment analysis, we can look at this one. I think we've looked at this sentence again. So we've looked at this previously. So unremittingly awful that labeling it a dog probably constitutes cruelty to canines. And so I run the model, and it says it's very confident that the sentence has negative sentiment, but we might want to know why the model thought this had negative sentiment. So if we interpret this prediction, wow, I'm not sure what's up with all these G's here, but that's strange. Anyway, we can see that the highlighted words here, the awful being the most highly ranked word here, makes sense why this was one of the most important words to predicting a negative sentiment. So this is a very simple technique for analyzing why a model is making a particular prediction. You just take the norm of the gradient with respect to, oh, I forgot to post the slides. Yeah, I'll post the slides right after the lecture. Sorry about that. But, you know, we might be interested in asking some more interesting questions about what these models have learned that aren't specific to just a single input example, because, you know, the model might agree with what we think it should focus on certain examples and disagree on other examples, and it becomes hard to know how exactly the model is reasoning about a more general phenomenon. So we'll go over, we'll spend more time in this lecture talking about the second of these 2 bullets, linguistic probe tasks, but first we can go over some other visualization-based approaches. So probably the most prominent example of visualization-based analysis was with the very first GPT model that OpenAI released. So they trained, I believe, like an LSTM language model or an RNN language model just to predict the next word. And then they discovered that a single neuron in their RNN seemed to be highly predictive of the sentiment of the input. So if you pass in negative reviews and positive reviews and plot the value of this single neuron, you know, out of like probably millions or tens of millions of neurons, the single neuron here seemed to, you know, be able to detect whether the review was negative or positive and do it correctly. And this is, as you can see in the caption, a character level RNN. So it's pretty interesting that this particular neuron seems to have learned you know, a more semantic global phenomenon about the text that is certainly not expressed at the character level. So this is one of the examples of successes of visualization. However, it's very difficult in general to find a single neuron that is solely responsible for modeling some phenomenon like this. In general, you'll have a subset of neurons potentially distributed across multiple layers that all work together to signal a particular phenomenon's existence or process that. And it's hard to quantify many of these things in the way that they did here with sentiment. So in 2017, there was a kind of toolkit released to visualize LSTMs. So these are more complicated types of recurrent neural networks, and they have many different weight matrices for the recurrent update. There's many sorts of, there could be deep LSTMs with multiple layers. There's embeddings and so on. And so I'm not going to go over how this particular thing works, but I just wanted to highlight that this is a very complicated visualization, and it will take a lot of time to get some actionable insights out of a tool like this. So yeah, there are lots of limitations with visualization. This tool aims to visualize every neuron in the network, or at least a thresholded set of neurons. So, you know, if we take something like GPT-3 with almost 200 billion parameters, it'll be very hard to scale up such a tool to something like that and find meaningful patterns through these kinds of visualizations. That said, people are working on these kinds of things, but it's a good segue to our actual topic of the day, which is linguistic probe tasks. So the setup here is that we have a phenomena of interest. We have some phenomena maybe of interest, and we want to know whether a model that we've trained or pre-trained has understood that phenomenon, or to what extent has it understood that phenomenon. So the setup is basically that we take our model, we freeze its parameters, and we only train a simple classifier on top of our model's representations, like its final layer representations, to predict whatever property we care about. So there's no further fine-tuning of the model that we are probing done. And the classifier that we're training is often called the probe network. And there are good reasons to keep the probe network as small as possible, as we will discuss later. So let's take a look at a simple example of what this could look like. So let's say I have some model, say BERT, for instance, that gives me a representation of a sentence. And so I can, get a representation of a sentence by simply passing it through BERT and extracting the CLS token vector. So given this vector, I'm now going to feed the vector into a classifier. So this could simply just be a linear layer over the final layer CLS token representation, and followed by a softmax. And this probe network then would be the parameters would just consist of a single matrix, so it would be pretty small. And we can make this classifier do a number of things. So in this particular task, we're going to have it try and predict the length of the input sentence. So how many tokens are in the input sentence? Of course, this depends on the tokenization that you use. But you can frame this as a classification problem by binning the sentence lengths into reasonable bins. So maybe the classes could be the sentence is of length up to 5 tokens, or 5 to 10 tokens, or 10 to 15, so on. So you can reduce the label space by increasing the size of the bins if you want. It depends on how much data you have. So Anyway, the point of this is to see whether the final layer representation, this blue vector here, encoded by BERT or whatever model that we're interested in probing, does this representation capture sentence length, which is, an important property to know about any input sentence. So during training, we can of course make arbitrary data for this task, right? We just need random sentences and we know their lengths. So when we train this classifier, we are not backpropping into the blue part here, the BERT or whatever model this is. The only thing that's getting trained are the parameters of this classifier. So it's not like normal BERT fine-tuning in which the error signal would propagate down all the way into the base BERT model. And the reason for this is because we are interested not in maximizing our score of this task of sentence length prediction, but rather we want to know how well this fixed blue vector can do at predicting the sentence length. So in contrast to all of the other tasks that we've discussed to this point in this semester, here our goal is not to maximize our performance. It's rather to understand more about what our model has learned. All right, and as usual, feel free to type questions into the chat. So we can do this same thing for many other tasks. These animations got messed up. So we can do it for word content, where we have a representation of a sentence and we have a representation of a particular word or token. So this could just come from our embeddings, our token embeddings that are part of our model. And we can feed both of these into a classifier and ask, does this word that is represented by the vector on the right occur anywhere in the sentence whose representation you've computed on the left? So this is a classifier that has two different inputs, a sentence and a word. And it's obviously important to know if the model knows exactly what words are in the input sentence, because this is a compressed representation of the sentence. So perhaps some of the words in the sentence it doesn't know about, but important words it does. So you can set up your word content task in this way. So this word, if we're using BERT, right, this would still be the CLS token representation on the left, and on the right we could use a subword embedding for the particular token that we're interested in querying. Oh my god. Okay, so another task, these were all presented in this Adi et al. Paper back in 2017, is word order. So if we have a sentence and we are given two words in that sentence, can we have the classifier predict whether the first word occurs before or after the second word in that sentence? So here we have three different inputs to the model, but we're still just training a binary classifier. So all of these are just focused on very basic properties of the sentence, and the thing that is getting probed in all of these tasks is the sentence representation. Okay, so this has been extended to many other types of tasks. So specifically in BERT and Roberta and other models, we not only get sentence representations via the CLS embedding, we also get token level representations. And it could be interesting to know what those token level representations are actually learning. So one task you might consider is, given the token level representation, can you predict a part of speech tag for the corresponding token? So does that token level representation encode information about the part of speech? because, you know, it's gone through many layers of self-attention. It's been fully contextualized with the rest of the sentence. So you might imagine that information that is low level about a particular token is lost during this process, but it would be good to know. There's also segmentation tasks such as NER. So that's named entity recognition. Given a token, can we predict whether or not it's a named entity or part of a named entity? And finally, we can create probe tasks by using syntactic structure, syntactic parsers. So we'll talk more about this latter one in a bit to make it more clear. But you can pass in two representations of two different tokens and then ask a classifier to predict whether there is some sort of syntactic relationship between those two tokens, or what is the nature of that syntactic relationship. All right. And finally, maybe more complicated one is you might want to know what the model has learned about certain spans of, oh, the video is lagging. Okay, I hope it picks up soon. It still says it's, okay, looks like it picked up. Sorry about that. My home internet is clearly not as good as EDU Roam. Anyway, for this task, we're interested in knowing what specific spans have captured, what kind of knowledge have they captured. And so here, you might get these token level representations, but you don't have a good way of computing representations for arbitrary spans. So you might have to define some sort of aggregation function on top of these token level representations before then performing a task such as this one, which is asking whether two spans of tokens refer to the same entity. So this is a coreference type of task. All right. So just to review the motivation of all these tasks, now that we've outlined several different specific instances of probes. First, if we can train a classifier to predict a property of the input text based on this frozen representation without any further fine-tuning of the model, that means that this property is likely encoded somewhere by the model. So the model has learned things like coreference or entities or part of speech that's present in the representation. However, if we cannot, so if the classifier struggles to predict whatever property we are interested in, then the property is either not encoded in the representation at all, or it's not encoded in a useful way, or where useful is kind of a comment on the relationship between the complexity of the probe network and the task. So if you can't extract the information about your probe task given like a simple linear classifier, which is how we are basically using all of these BERT representations, we're just popping a classifier on top of it to solve all sorts of arbitrary tasks, then perhaps whatever property it is, if we can't extract it from a simple classifier, then it's either encoded in a very complicated way that downstream tasks may not be benefiting on, or it's not included in the representation at all. So that's a general idea. And note that these probe tasks don't require any sort of visualization of the neurons or stuff like that. This is a training-based approach. So we're training simple classifiers to understand how they perform. And based on their performance, we can conclude various things about what the model has and has not understood. So as you saw, These probe tasks are usually framed as very simple classification problems. They're often binary classification problems that focus on simple linguistic properties like part of speech or things like length or word content. They're intentionally designed to be simple to minimize problems with interpretability. We want to be focusing on one very specific low-level question, not a broader one that kind of conflates many different linguistic properties together. Okay, and the fourth bullet is quite important. So the probe task, the probe classifier, is independent of the encoder architecture. So you could try varying the complexity of your probe network. You could use a simple one-layer classifier, or you could put a huge deep network on top of the BERT representation to classify whatever property that you're interested in. However, there might be issues with doing the latter, as we'll talk about later. So this slide is just an overview, just to make things as clear as possible about how this works. So the blue part here is your encoder model, like BERT or Roberta, the model that you're interested in probing. And so you can see that the blue model here is not fine-tuned. So whatever it is after pre-training, that's how it's always going to be during the probe process. We are interested in learning about how this blue network is operating. So we have this classifier that's put on top of the representations that are output by our blue network. And this classifier is the thing that's actually trained during the process of training the probe task. Okay, so hopefully that's clear. If you have any questions, please type them in the chat and I will answer them. All right. So there's many different types of probe tasks that I've not covered that are maybe a little bit more interesting. So we'll talk about arithmetic probing to see how much these models can understand numbers and numeracy. There's syntactic probes and also knowledge related probes. So can these models, how much factual knowledge do they have? But one kind of finding from all these probe tasks that has been pretty commonly reported is that the lower level layers of these models focus mostly on syntax, like low-level local syntax, things like part of speech or like low-level parsing, stuff like that. And upper layers tend to focus more on semantic content. I see there's a question. Does the model have to be an encoder or can we use any model? So as long as your model gives you vectors of tokens or sentences, you can apply it in this fashion. So it doesn't have to be an encoder. It could be a left to right language model. You would just want to be kind of careful about how you set up your probes so that they are independent of whether the model is a left to right LM or whether it's like a fully attentive encoder model like BERT. Okay, train only classifier layer, is that means transfer learning? I'm not sure what that question is asking. So yes, in the probe task, we are training only the classifier layer. Here our objective is not to, transfer knowledge to better solve some task. The classifier's role is to try and explain what the base model has learned. So it's kind of a different purpose. Okay, so there was this paper by Ian Tenney and some colleagues on how BERT within its layers has essentially learned the traditional steps of the NLP pipeline that people used to do pre-neural models. So we haven't covered any of these kinds of models, but before any sort of representation learning approaches became popular, if you wanted to do natural language processing, you basically would have to extract a bunch of features from your text. And you would feed all of these features into a classifier like a logistic regression or an SVM type model to predict whatever it is that you wanted to predict, like sentiment, for example. So features that were commonly useful are things like part of speech, parse related features, whether things are entities or not, what kind of semantic roles they're playing, and when do they refer to the same entity or event. So this is kind of the steps of the traditional NLP pipeline. And usually to do something like parsing, you would probably need to do part of speech tagging. To do named entity recognition, you would probably need to do parsing first. So all of these things kind of build on each other and take each other as inputs. So I'll get to this question after covering this plot, the probing model. So basically like the best layer to solve this particular task. And they have all of these tasks from part of speech tagging, which is very low. Constituency parsing and dependency parsing are still kind of low level syntactic tasks. Then you have things like entity recognition and semantic role labeling and coreference. Here you start getting into more higher level semantic understanding. Things like relation extraction and so on require more semantic understanding. So you can see here that the low level syntactic tasks tend to have an expected, so the model, if you extract the representations at layer 3 or 4 of BERT, those perform the best, not the layers that are higher up. While for tasks that are more complicated, like coreference or relation extraction, you need to go higher up in the network before you can solve that task. Pretty interesting, and kind of confirms the finding that the lower level layers of BERT are more focused on local syntax and the higher level layers on more high level semantics. All right, so let's take a look at these questions. So for the actual task of part of speech tagging, we would fine tune, right? Or such a probe network suffices. Yeah, so if you actually wanted to solve part of speech tagging, let's go back here. If you actually wanted to solve part of speech tagging, you would not only train this classifier, but also fine tune into the BERT network that is creating these blue tokens. So the probe network alone would probably give you some decent performance, but you would get better performance likely by fine tuning the entire model, as we've discussed with normal BERT fine tuning. That's a good question. All right, is it possible to create probe networks without using a classifier? Like, can corrupting the input tell us whether the model has learned the word or not? So I think you should think more carefully about what kind of corruption can tell you something about the whether the model has learned a word or not. I imagine if you're thinking about BERT and a masked language modeling task, you could, for instance, drop words from the input until the model fails to predict a certain word correctly in a masked slot. But this is more analogous to the gradient-based visualization of the input, and not so much related to a more general property of the model. Like, sure, you can try a bunch of examples and see just through simple corruption if you can understand what the model is doing. but it's hard to learn about things like part of speech or co-reference through this kind of corruption process. All right, so let's take a look at 2 or 3 different specific examples of probe tasks in more detail. So we might be interested in understanding whether BERT encodes this tree-like structure of language, which it helps us out in understanding different meanings of a particular sentence and which one is more likely. So here, the chef who ran to the store was out of food could be interpreted potentially in a couple of ways. So you could imagine the more likely interpretation is the chef is out of food, and that's the reason the chef ran to the store. But an alternate interpretation is that the store was out of food, which wouldn't make as much sense here. But you can see from this tree that, so this is a dependency tree of the sentence. The distance in the tree was and the chef is, well, they're just neighbors, right? The distance between was and store, though, is a much longer path through the tree. So this indicates that was out of food is modifying chef and not store. So given this kind of tree, which we can get from a dependency tree bank where people have manually labeled, created these trees out of the sentences, we can ask the model, given 2 tokens in the sentence, can we predict the distance between those 2 tokens in the tree? And can we also predict which one is deeper down in the tree, which of the 2? So these are 2 tasks that, if we can solve them, we can essentially even reconstruct the tree from these 2 tasks. So this paper from Hewitt and Manning in 2019 basically proposed these 2 probe tasks. So figuring out what the distance in the tree, like the path length, is between 2 words in the tree, and also the depth of the tree, the depth of a particular word in the tree. So you can formalize this as a probe task where, given a sentence representation and the representation of 2 words in the sentence, predict how far away in the tree they are. And then also predict, given any word and the sentence representation, how deep in the tree that word is. So the conclusion from these tasks on BERT is that yes, it can actually recover these trees despite not being actually trained with any sort of tree-like information provided to the model, right? BERT is given just a flat encoding of the input sentence. It has no tree structure, and yet it seems to be able to induce this kind of tree structure in its parameters somehow. And perhaps this structure is actually useful for BERT to solve its pre-training task, which kind of makes sense. Okay, I see a question. From these BERT probe tasks, can they handle garden path sentences? That is a good question. I highly doubt they can, but garden path sentences are often confusing for humans to process, let alone models. But yeah, I mean, it's there have been works that examine BERT and language models more specifically, like left to right language models on garden path sentences. Usually you can set up tasks such that you give a model part of the garden path sentence and ask it to predict like the next word. And given one representation of the sentence, or given one interpretation of the sentence, one word makes sense to predict. But if there are alternate interpretations as well. So that's generally how those works are done. Although Yeah, I'm not sure specifically about BERT. All right, so that's enough about syntax. Another interesting thing to probe for is numbers. So does BERT understand, for example, that 11 plus 14 is 25, just from its mass language model pre-training objective? So you can set up several different probe tasks to test these models' understanding of numbers. In this paper by Eric Wallace and colleagues, they input in this list maximum task a list of 5 numbers. They passed it through something like BERT, then passed it through a probe network, which here is not a simple linear classifier, but rather it needed to be contextualized. So it's some sort of LSTM. And then the model would have to predict a 0 for everything except the maximum element in the list, which it would have to predict a 1 for. So here, 9, 4, 12, 1, 11. 12 is the biggest number in this list, so the model should output a 1 here and a 0 everywhere else. Another task is just translating a number written in natural language into numerical form. So given NINE, this token, we would pass it through our BERT model and then put a regression model over this. So this could just be a simple linear layer that instead of putting a softmax over it, we put a square loss over it to predict the actual value of this number. So the target here is 9.0. The model produces 8.5. You know, does it really understand what 9 is? Maybe approximately. And finally, you can even do like simple math here. Like you can input 2 numbers, 7 and 2, and train this like addition regression model where the model is trained to, the probe model, this MLP, is trained to output the sum of the 2 numbers, like the numerical value. Oh, I see a question about the previous syntactic probe task. So it's where are we getting the trees from? There are many data sets that contain these trees. So like linguists have gone through and created trees that look like this from sentences. So most of these probe tasks are run over those existing data sets. You can look up universal dependencies. That's a pretty popular data set. We'll talk more about parsing later in the semester. All right. So back to our numeracy probing. It turns out that Elmo is actually better than BERT at understanding numbers. So we see on this list maximum task, if all the numbers are between 0 and 99, Elmo is 98% accurate at classifying which of the 5 numbers is the biggest. If the numbers are bigger, though, all of the the performance seems to drop. And it turns out that both Elmo and BERT are actually worse than an untrained convolutional neural network. So kind of suggests that these models are not particularly good at understanding the values of numbers. For the decoding and addition tasks, you're just reporting the squared error because these are regression problems. You can see that the error gets bigger and bigger as the numbers get bigger and bigger. But yeah, Elmo has a lower error than BERT on most of these tasks. And so the reason for this is something that we probably didn't spend too much time on, if any, this semester at all, is that Elmo's input layer is actually a character level convolutional neural network. So it doesn't start with subword embeddings like BERT does. It actually starts with a character encoder, then followed by word level RNNs. So the takeaway of these experiments is that models that are at the character level understand numbers way better than models that are at the subword or word level, which makes a lot of sense because like the subword encoding, the byte pair encoding that we learned about has nothing specific to numbers. So some numbers could be represented by a single vector, even if they're multiple digits. Other numbers might be split up into multiple different digits. And so it's not consistent. But in a character level model, it's always going to just be represented as a sequence of digits. So yeah, if you're interested in having a language model that's also like, capable at doing some math or something like that, you might consider a model like byte T5 or other character level things that we've discussed. All right. So the last type of probe task we'll talk about is whether BERT actually understands world knowledge. So can we query it in such a way that we give it a triple, right? So like entity 1, relation, and then have BERT predict entity 2. So here we have Dante was born in what location? And if the model knows this fact, then it would it would produce Florence. Okay, so you can obviously create these kinds of questions by looking at an existing knowledge graph where people have encoded manually or automatically all of these different relationships between types of entities like Dante and Florence. And given a relationship that you get from, say, a knowledge graph, you can transform it into a masked language modeling instance, like Dante was born in Mask. And if the model has learned this, it should predict Florence for the missing token. So this kind of knowledge-based probing requires manually defining some kinds of templates for certain relations. So if you're interested in probing the place of birth relation, you might create this template, S was born in O, and then provide S and see what the model predicts for O, or vice versa. And you can also use questions. So if you have a question like who developed theory of relativity, you can rewrite those as the theory of relativity was developed by Mask, so that you can use this as a prompt to a masked language model like BERT to see if it can produce Einstein there. So here are some examples for different types of relations. We can see what BERT actually produces here. So, we have relation P54, which seems to be sports related. Dani Alves plays with Mask. If the model knew this, it would produce Barcelona, I guess at least at this time, but it didn't know that. Here we can look at iPod Touch is produced by, so this is like a product company relation. The correct answer is Apple, and the model's first highest ranked, most probable prediction was also Apple. Similarly, Bailey Peninsula is located in blank. Antarctica was the correct answer and also the model's most preferred answer. So you can see here some of these questions the model is pretty good at. Others, like JDK is developed by blank, it is not good at, which you can kind of use as a proxy for whether the model has understood this particular fact or not, or memorized it from its pre-training data. Also note that this kind of prompting is pretty complicated when you have subword level models, because if, for example, wasn't a single token in the vocabulary, but split into multiple subword tokens, then you would have to actually produce multiple mask tokens in order to properly be confident that the model wanted to produce Antarctica. So here, I think all of these questions are designed so the right answer is a single subword. So you can see some other non-knowledge, these are more common sense based ones. Ravens can blank, so fly, fight, kill, die, hunt. These are also things ravens could do, but fly is the one of the correct answers, at least. Okay, so in this paper, they basically found that BERT does contain, despite not having an explicit knowledge graph, and it is a promising way to encode all of these kinds of facts, even though we can't pinpoint exactly where in the network, Dante's birthplace is located. It is there somewhere. We can find it through these kinds of input-based probe tasks. So that's pretty cool. And, as these models have been scaling up to bigger and bigger and bigger model sizes, we see an increased memorization ability from them. So they're able to store far more knowledge from their training data. So yeah, one potential way of encoding a lot of knowledge. Okay, so the last thing I wanted to talk is the complexity of the probe network. So stepping back from specific probe tasks, now that we've talked about a bunch, one important question is, how complicated should the probe network be? So this classifier that we're putting on top of BERT or whatever, how big and how many parameters should that network have? Okay, so there's an argument both for simple probe tasks as well as complicated probe tasks. First, with simple probes, we basically want the ability to find information that's easily accessible in a representation, because this tells us whether or not a downstream model can make use of this information easily. However, we might also want to know whether a property is encoded at any level, however nonlinearly or complicated this probe task, this probe property is encoded. We want to know whether it's there at all or not, regardless of how easy it is to access. So that's basically the question. Oh, I see a question in the chat. A query can be rewritten in many ways, which can influence the output that we get. Yes, that is very true. So if I wrote, JDK is developed by blank, and it got it wrong, but then I could also have rewritten this as blank developed JDK, and maybe it gets it right there. That would indicate that the problem is not in the model, but in the template that is being used. The model might be able to understand one phrasing better than another. And so, yeah, that's definitely a problem. I think people have dealt with this by making multiple templates and aggregating over those, or using paraphrase type models. But yeah, definitely a good question. It could definitely mislead if you're using just a single template. How should the training data for probe tasks be designed? Can you share some guiding principles for training data? In general, like you want to use, so yeah, it depends. Like, there are probe tasks for which there are huge training data sets. There are probe tasks for which there are small training data sets. I don't think there are any, like guidelines on how big something has to be, or, but yeah, at least, the data should be high quality. As you can see in all the examples that we've discussed, there's also variation in whether or not the probe task is self-supervised, in that, like, for example, sentence length is something I can create infinite data for just by getting arbitrary sentences. But this kind of knowledge-oriented probe is not, right? This actually requires me to have some existing data set that has all of these kinds of relations between entities so that I can convert them into these query statements. So yeah, there's a huge variation. I don't think I can make any general recommendations. Yeah. Okay, so let's get back to the probe complexity. One potential issue with a complex probe is that the probe network could be, get really big and might be able to predict different properties that don't even really exist in the original representation. So like most of the work is actually being done by the probe network, and the original input is not contributing as much. So that's a kind of challenge that was tackled by this paper by Hewitt et al., which is one of the readings for today. This paper proposed the idea of control tasks to kind of balance the probe complexity as well as the performance of the probe task. So just to explain this concept, let's say that we are designing a probe for part of speech tagging. So given a sentence, we want to know whether the final layer representations of each token encode the part of speech of that token. So like, does the model know that this token is a determiner and that this is a noun and that this is a verb and this is an adverb? So the normal way of doing this is just to feed these representations into a classifier, to ask the classifier to predict the part of speech of the corresponding word and look at the accuracy. So the way in which this paper does it is they train a part of speech probe, but they also design a control task to kind of balance out the probe complexity, the probe network complexity. So in the control task, they take their vocabulary and they partition it into some random subsets where the number of subsets is equal to the number of part of speech tags that they have. So let's say there are 42 different parts of speech in their data set. They make 42 different subsets of their vocabulary. And these are done at random, so they are not grouped in part of speech. So here we have, in cluster 15, quickly and dog belong to this label, even though quickly is an adverb and dog is a noun. And here in label 42, we have an exclamation mark and after, even though those are obviously different parts of speech. So basically what we're going to do is train one classifier for part of speech tagging and one classifier for this control task, which is just given the representation of this word, can we predict which of these random groups that it belongs to? So if the model is able to predict which random group the word belongs to, then that's a sign that the probe network itself is probably too complex, because we're not actually learning anything about the representations here. These are completely random groupings. So the probe network is doing all the work in recovering these groupings. So this is just a description of what I just said. We're making this kind of control task where the behavior is different and kind of random instead of defined by a part of speech. So the findings from this kind of control probe are that there are two things about a probe task that you care about. So we have talked to this point about accuracy being important, right? Because that tells us whether or not the model has understood the property that we're measuring. So here we see that the light blue line up here is showing the part of speech tagging accuracy. The red line on the bottom is showing the accuracy in this control task of predicting which random group this word belongs to. So, and then on this plot, the x-axis is showing it's varying the complexity of the probe network. So this is just the number of hidden units in the MLP, the multi-layer perceptron, which is just a classifier network. So like how many parameters are in my probe classifier. You can think of it that way. So you can see that if the probe classifier only has 2 hidden units, the accuracy and part of speech tagging is above 80%, so it's not that bad. But the accuracy in this control task is around 40%. So the gap here is very big, which indicates that the part of speech information is kind of easily accessible here. And even with a very simple probe, we're able to pick up on it. Whereas this random grouping cannot be learned from this probe network because it's too small and not powerful enough. So we can see that with 1,000 units in our probe classifier, the part of speech tagging accuracy is above 90%, but the control task has also gone over 90%. So this is an uninformative data point here, because this is saying that this probe network could have fit any sort of random grouping of your vocabulary. And just because it got a good performance on part of speech tagging does not mean that it actually understands part of speech tagging. The probe network could just have learned any sort of grouping, so it doesn't tell you that much. So essentially, when you're doing a probe of one of your models, it's good to have one of these control tasks if you're able to design it. And that is a pretty big caveat, because it's hard to design these kinds of control probes for every single phenomena that you care about. But you're looking for cases where you're getting high accuracy on your probe task that you care about, but then also there's a big gap between the probe accuracy and the control probe accuracy. And that's called the selectivity here, the actual difference between these two things. Okay, so hopefully that's clear. This is a pretty clever way of figuring out what is the optimal size of your probe network. So you want it to be good at classifying the phenomena that you care about, and bad at classifying something that you don't want it to learn, like some random grouping of words. Okay, so this is basically showing that different probe networks can give you comparable accuracies, but have very different selectivity. So here is a multi-layer perceptron with 1 hidden unit, giving you 97% accuracy on part of speech tagging, but very low selectivity. So the difference between the control task and the probe part of speech tagging accuracy is low, whereas without a hidden projection here, so with just a linear layer and no nonlinearity, the selectivity is much higher, meaning that the control probe accuracy is lower. Okay, so I just want to wrap up by also mentioning that one useful thing about these probe tasks is if you develop a probe task and you find that your model isn't actually good at it, so let's say BERT, for whatever probe you devised, seems to be failing on that probe, so its representations are not encoding whatever property it is that you're testing for, then you can actually try and inject that knowledge into your base model, like BERT, by fine-tuning the entire BERT model with this additional probe objective. So here is an example of the loss function, where you have the original masked language modeling objective of BERT, and then you also add the loss function from this probe objective with some hyperparameter that's controlling the interpolation weight. So how much weight do you give this probe versus the masked language modeling accuracy? So no Bert is one example of this, where they found that Bert hadn't learned certain facts about entities like prints, for example. So during the mask language modeling training, they also added some objectives to ensure that the model learned some relationships between certain entities in a knowledge base. So yeah, that's one way to move forward. Although, as we also discussed, another way which seems to be more and more popular in industry these days is just to train bigger and bigger models and more data, because as we'll talk about later in the semester, there are some advantages of bigger models where they seem to be able to memorize things faster and not see them as much during training, and they have way more capacity to memorize many different facts. So that's another alternative as well. All right, so that's all I had. I see no additional questions. Sorry about any issues with the video, and I will see you on Wednesday.